All right, so we are going to work through test 4, lesson 3. My bad, y'all. And I hope my thing doesn't glitch the whole time. It'll aggravate me. Okay, hang on. Let's restart this. Hopefully that's better. Okay. All right, so we're going to talk about trig substitution. So now that you can find integrals involving powers of trigonometric functions, which was test 4, lesson 2, all right, you can use trig substitutions to find integrals involving the following radicals: the square root of a squared minus x squared, square root of a squared plus x squared, and square root of a squared, x squared minus a squared, where x is your function and a is some value. Okay? And basically what we're going to do is we're going to use the objective to eliminate radicals in the integrand, and this can be achieved by using the following Pythagorean identities. All right, so remember, if we're trying to eliminate the radical, the easiest way to eliminate a radical is if the value underneath it, or if the term underneath it, is a squared term. So that's why we're using these, because whenever we take the square root of cosine squared, we would end up with cosine. Okay, so kind of like power reduction in a way. All right, everything you need is already filled in on your foldable. There's a couple of things that we'll reference in here, but they are already in your foldable, so you don't have to put them in there. All right, so example number 1 says use the Pythagorean identities to simplify a squared, the square root of a squared minus x squared, but let x equal a sine theta. All right, so what they want us to do then is they want us to go in here, and where I see x, I'm going to put a sine theta. So we're starting out with the square root of a squared minus x squared. Okay, so I'm going to simplify that into my substitution. A squared minus a sine theta is my x. Okay. And then we're just going to keep going from there. Okay, so I have, if I square that, right, I have a squared minus a squared sine squared theta. Then from this point, I could factor out an a squared, and I would be left with 1 minus sine squared theta, which, using our trig identities for Pythagorean, okay, we know that 1 minus sine squared is the same thing as cosine squared. So then if I take the square root of a squared cosine squared theta, I get a cosine theta. So that's what they were asking us to do. All right, and our parameters over here were between negative pi on 2 and pi on 2. Okay, so that's going to be in quadrants 1 and 4. And if you think about it, your cosine value is your x value in quadrant 1 and 4. That x value is going to be positive. Okay, so we're good there. All right, note the restrictions on theta ensure that the function that defines the substitution is 1 to 1. And 1 to 1 meaning it passes both the vertical and horizontal line test. Okay, it has to pass both the vertical and the horizontal line test. That says vertical. Sorry, y'all. Okay, these are the same intervals over which arcsine, arctangent, and arcsecant are defined. Because if it's 1 to 1 for sine, cosine, tangent, that would be the same way for arcsine, arccosine, and arcsecant. All right, so we're going to move on to example number 2. Okay, find the antiderivative of dx over x squared, square root 9 minus x squared. All right, well, just so you know, a lot of times when you're looking in your book, things of that nature, you're going to see it written like this, or a lot of places that write it, they put that dx on the top. That's the same thing for what we usually write as the 1 over x squared, square root of 9 minus x squared dx. It's the same thing, okay? So we can rewrite it however we choose to rewrite it. I just like to have that dx out to the side, but a lot of books, a lot of text, you'll see the dx on top. All right, so we're going to talk about our prep work with this. And I mean, these do look familiar to some other ones that we've used before. Okay, so we're going to talk over here about our prep work. So if we're using this, okay, then the 9 is going to be our a squared. Therefore, our a is going to be 3. All right, and now we're using number 1 here. We're using number 1 here, like what we did up here in number 1. So we're going to let x equal a sine theta. All right, and an a in this situation would be 3. So we're going to let x equal 3 sine theta. All right, therefore our dx would be 3 cosine theta d theta. Okay? Now, if I go from here, and y'all remember, I'm probably going to talk faster than if we were in class because there's nobody asking me questions and so forth. So y'all kind of have free reign. If you need to pause this video to catch up on the math or whatever, you can do so, rewind it, just put somebody in charge of that. All right, so now I'm going to look over here, and I'm going to write this using what I know. Okay, so x squared, so x for us is 3 sine theta. So we're going to do the integral 1 over, so x squared will be 3 sine theta squared. And then our dx is 3 cosine theta. I got to put my 9 minus x squared in there first. Okay, so let me show you that math. Sorry, I could have just done the skip on that, but I didn't. Okay, so I've got the square root of 9 minus x squared, right? The square root of 9 minus, and we're using x squared to be 3 sine theta. My bad. All right, so now if we simplify this out, okay, that's going to give me the square root of 9 minus 9 sine squared theta. Again, so all I did was I substituted my x into here, okay, and I'm going to write all this out over here and then just put it in right here. All right, so then I could factor out my 9. So that'd be 1 minus sine squared theta. And then we know sine squared theta is cosine, so that's going to end up, square root of 9 is going to be 3, and that would be cosine squared theta. So if we take the square root of cosine squared, it's just going to be cosine. All right, so this whole thing right here simplified to 3 cosine theta. So I'm going to put that in right here as well. And then times dx, and our dx for us is 3 cosine theta d theta. All right, so then you're going to see that our 3 cosine thetas are going to cancel out. All right, which leaves me with the integral of 1 over 3 squared is 9 sine squared theta d theta. All right, well, we know 1 over sine is the same thing as cosecant. I'm going to pull that 1/9 out. And that will leave me with cosecant squared theta d theta. All right, so we want to take the antiderivative here. But if you go in your flip book, and I'm not going to pull my whole flip book out, well, I might do it later, but I did just write this down to show you. But if you go to your flip book and you look at your derivatives and your derivatives and integrals, and antiderivatives, what you've got here is this is the one we're going to use. Okay, we know that cosecant squared, the derivative of cotangent is cosecant squared. Okay, so we've got the cosecant squared. So we're going to go to cotangent, but the problem is we don't have this negative. But remember, we can make that negative there. Just pop a negative on the inside, pop a negative on the outside. So then if I take the antiderivative from there, that's going to get me to negative 1/9 cotangent theta plus c. Okay, so that is my antiderivative of my original problem, okay? However, the problem that you have here is that we are in terms of theta and everything up here is in terms of x. Okay, so we've got to figure out a way to make that go back. All right, so you got a triangle down here. All right, so if we know that x equals 3 sine theta, so let's look over here at our triangle. If we know that x equals 3 sine theta, then we know that the sine theta equals x over 3. Remember, sine is opposite over hypotenuse. So if this is my theta, my opposite would be x, my hypotenuse would be 3. And then if we did Pythagorean theorem, right, a squared plus b squared, all that kind of stuff, all right, you'd be looking for this side. It would end up being the square root of 9 minus x squared. Because 9 would equal x squared, whatever this is, x squared plus whatever the square of whatever this is, and we work backwards and get that, okay? So using that, if we go back over here, so now we're going to convert this. So the triangle on the right can be used to convert thetas back in terms of x. So we've labeled our triangle. All right, and we started off with -1/9 cotangent theta plus c. Remember, tangent, and this is the whole throwback. Okay, tangent's opposite over adjacent. Therefore, cotangent would be -1/9. And I'm going to write this out. I don't do this normally. Y'all don't have to do this. It'd be adjacent over opposite plus c. So in this situation, our adjacent to our theta is going to be this side down here. So it's going to be negative that side down there. -1/9 times. That side is 9 minus x squared. And then opposite would be x plus c, which is going to simplify to just negative the square root of 9 minus x squared over 9x plus c. Okay, so now you have taken your original function that it gave you, use your Pythagorean identities, letting a sine theta be x, gone through everything and gone back into your x. All right, so it's a lot of the same work, just in different ways. All right, so let's go up here to the top. And what you're going to see up here at the top is all this is already in. I think we left this part out on your flip book, but I'm pretty sure we have the substitution, the expression, what it ends up equaling, and our domain for that in your flip book. And that's what we're going to refer to. I'm going to leave these up here just because we're going to use one of these in example 3, and I'm going to reference it, like draw some arrows and reference it from here. All right, but that is in your flip book on your trig substitutions right here. This one right here. That's what you're using. Okay, and there will be some time where it's easier just to say, oh, it simplifies down to blah, 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 instead of us doing the math for that by looking at that flip book. All right, so let's look at example number 3. They want to find the antiderivative of 1 over the square root of 4x squared plus 1. All right, so let's look first. First, we want to recognize that 4x squared right here is ultimately 2x quantity squared. Okay, so that will be like an x squared and an a squared if we did that. Okay, so we do have the square root of x squared plus a squared. And remember, we're adding, so it doesn't matter. We're really going to look right up here at this second line. Okay, so if we're going to utilize that second line, then our prep work is going to be that a squared equals 1. Therefore, our a equals 1. All right, now this time our x is 2x. Okay, so right here, our x is 2x. So 2x equals a is 1 tangent theta. They use t's instead of thetas. I like thetas because they don't look like pluses or anything else, so I like to keep my theta in there. All right, therefore, if we did the derivative here, then 2 dx would equal secant squared theta d theta. And if we solve for dx, basically our dx is going to be 1/2 secant squared theta d theta. Okay, and if you look here, so now when we decided that we were using this row, right, this whole thing here is going to simplify to this, is what they're saying. So we can simplify the square root of 4x squared plus 1 to a secant theta. So in that situation, we're going to come down here. So we're going to take the integral of 1 over our a is 1 secant theta. And then our dx is 1/2 secant squared theta d theta. So now we've done our substitution. We know what dx is. Went in for dx. We know using our flip chart or this line right here that if we had this function here, we're using the substitution that x equals a tan theta becomes a secant theta. All right, I'm going to do that math real quick over here just to make sure everybody's with me on that. Okay, so if I had the square root of 4x squared plus 1. Okay, and 4x squared for us is going to be tangent squared theta plus 1, which came into secant squared theta minus 1 plus 1. Then the 1's cancel, which gave me just secant squared theta, which ends up being, y'all know I ain't got white out at home either. Messing me up. It's going to be secant theta. Okay, but again, we can go, this is the math for this, from here to here using your chart. Okay, just looking right here. We can go from here to here without having to do this math, just using our chart. All right, so from here, we're going to pull out that 1/2. Secant squared, so one of those is going to cancel with one of those. So I still have a secant on top. Okay, and I got the 2 on. We'll pull that 1/2 out, so it's just going to be secant theta d theta. All right, and then from here, we're going to go to our foldable. And we're going to fill in the fact that we know that's going to equal 1/2 natural log of secant theta plus tangent theta plus c. Okay, so now we have done the antiderivative part. And now remember, from here, we have to go back to our x's. So we're in thetas, and we've got to go... We got to go to x. All right, so let's look down here. We'll draw us a little triangle. Okay. So we know that the tangent of theta equals 2x. Right? So that's ultimately this. Tangent of theta equals 2x over 1. So remember, tangent is opposite over adjacent. So our opposite is going to be 2x. Our adjacent is going to be 1. So square this, that's going to give you 4x squared. Square this is going to give you 1. Add them together. So this side is going to be the square root of 4x squared plus 1. And you're going to notice these are going to be the same. That's like the whole point, whatever you're looking for being equivalent. All right, so now we can go in and say 1/2 the natural log. All right, so secant is 1 over cosine. So remember, again, so secant's 1 over cosine. Cosine is normally adjacent to hypotenuse, so secant will be hypotenuse over adjacent. So hypotenuse is going to be the square root of 4x squared plus 1 over 1. So it's going to be the ln, absolute value of the square root of 4x squared plus 1 over 1. And then tangent is normally opposite over adjacent. We're going to go adjacent over opposite. I'm sorry, it's just tangent, so it's opposite over adjacent, so 2x over 1. So plus 2x plus c. So there is your final answer. Okay. Now, like if you were looking back through your notes, that SOHCAHTOA is just kind of stuck in there. It's just to remind you so that we can evaluate our functions the way they need to be. All right, so it is often the case that trigonometric identities are raised to a rational power. In this instance, it is better to rewrite the denominator, substitute, simplify, and then apply the appropriate trigonometric identity. All right, so rewrite the denominator, substitute, simplify, and then apply your appropriate trigonometric identity. All right, so here we go. Go up here. All right, so looking at example number 4, we've got the antiderivative of 1 over x squared plus 1 to the 3/2 power. All right, so if we rewrote this, okay, we could rewrite this as the antiderivative of 1 over the square root of x squared plus 1 to the 3rd power dx. Now it is in the form of x squared plus a squared. Square root of x squared plus a squared. Okay, so if we did that, let's look at our prep work. Okay, a squared would be 1, therefore a would be 1. Okay, and now if we're doing this again, go back to here. Okay, just looking back up here. Well, let me see if I can find find my flip book. Okay, so here we go. So if you're looking on your flip book, a squared x squared, this is the only one with a positive. Okay, so we're using x equals a tangent theta. We're going to simplify that to a secant theta. Okay, so that's what we're using. So we're going to say that x equals, a is 1, so it's just going to be tangent theta. All right, the derivative of dx is going to be secant squared theta d theta. So again, I can do the math where I put x in as tangent squared theta and go through the whole thing, or I can just go ahead and say here, I know that if I have this right here, x is going to equal a tan theta, and it's going to simplify to a secant theta. Okay, so if I know that, I'm going to end up over here with the antiderivative of 1 over. So this whole thing right here is going to simplify to secant theta. So that's going to be secant cubed theta. And then our dx is secant squared theta d theta. And now we're going to simplify those. So the secant squared is going to cancel with 2 of these, leaving me with the antiderivative 1 over secant theta d theta. And we know 1 over secant is the same thing as cosine. And then if we take the antiderivative of cosine, we know we're going to get sine theta plus c. All right, but again, now we're in theta, we need to go to x. So that's going to use our triangle over here. So we should know they gave us tangent. Okay, so using tangent theta equals x over 1 with our theta here. Opposite over adjacent, and then this side is going to be what we had, x squared plus 1. So using that, we know sine is opposite over hypotenuse, so that's going to be x over the square root of x squared plus 1 plus c. Done. Right? Then sometimes we must, okay, y'all, this is where y'all are like, yeah, it can't get any worse. Okay, complete the square. Which I don't think is super difficult. It's just not something we like to do. All right, so sometimes you must complete the square in order to obtain an expression by which we can use trigonometric substitution. In other words, we don't have anything that looks like this. Okay, we don't have anything that looks like this right here. Okay, but I can complete the square on this because, like, if I wanted to complete the square on just underneath the radical right now, okay, I would have basically that we want to say x squared minus 4x, and we'll set it equal to 0 right now, okay, because we're just completing the square, what it would be like. Okay, so remember, half of 4 is 2, so we're going to add 2 squared to both sides. So that's going to give me, on this side, then it would be x minus 2 squared is going to equal 4. So now if we move that over, we're going to get x minus 2 squared minus 4 equals 0. So now we can replace this with this. What I mean by that, instead of writing x squared minus 4x, we're going to write the square root of x minus 2 squared minus 4 dx. And if you think about it, if you were to work out x minus 2 squared, okay, when you square that minus 2, you're going to get plus 4. When you take away 4, you're going to end up without that last term, which is going to take us back to here. Okay, so mathematically they're equivalent, which is why they can do that. And now it looks like we're in the form of x squared minus a squared, which is what we want, one of the forms that are in our flip book. All right, so then in that situation, our a squared is 4. Therefore, our a is 2. And now our x minus 2 is not just x, it's x minus 2 would equal, and if we're doing x squared minus a squared, right? That's this one right here, x squared minus a squared. So we're going to be, x is going to be in the form of a secant theta, and we're going to simplify to a tangent theta. So a secant theta, a is 2. Then if we take the derivative of this, dx is going to be, so the derivative of this side is just dx, and then it's just going to be 2 secant theta tangent theta d theta. Again, we can go through all the math that gets what this is going to be, or this one, either one, okay, down to what it simplifies to. But you just said, if I have this, it's going to simplify to a tangent theta. So we're just going to simplify this to 1 over a is 2 tangent theta times dx, which is 2 secant theta tangent theta d theta. All right, we'll simplify this out. 2's cancel, tangents cancel. So I am left with the antiderivative of secant theta d theta. And if we look again, take the antiderivative of secant, we know that's going to be the natural log of secant theta plus tangent theta plus c. All right, draw my little triangle. Y'all probably have enough time to watch this video twice if you needed to. All right, so here's my theta. So we know right now that our, let's see, we were given x minus 2 is going to be here. 2 is going to be here. Then we know that this side right here is going to be that original, that x squared minus 4x. All right, I'm going to write it out one more time. Okay, secant's 1 over cosine. Cosine's adjacent, so that's hypotenuse over adjacent. So that's going to be ln. The hypotenuse here is x minus 2. And the adjacent would be 2 plus tangent is opposite over adjacent. So opposite is the square root of x squared minus 4x over 2 plus c. All right, so I'm going to have to pause this video here. This might actually be a 2 separate video situation because I've got to go handle something with Harper. So I'm going to pause this video here, and then I'll pick back up on example number 6. Like I said, because I'm going to have to actually leave, I'm going to stop it and then do a second video for the example number 6 because I don't want to risk me pausing it and being gone for a couple of hours and then it completely erasing what I've done. So we'll pause this video here. And then we'll pick back up on example 6 in a separate video.